problem 3.3, calculate the following limits, and we have 6 limits to calculate. Okay, easy enough. Okay, so let's go to each of them. First is the limit when n goes to infinity of the nth root of a to the n plus b to the n with a, b greater than 0. Okay. Okay, first of all, the first thing that comes to mind in my mind is that if you have this, you have if a is equal to b, right? This is reduced to this limit when n goes to infinity of n, nth root of 2a to the n, right? And this is equal to the limit when n goes to infinity of the nth root of 2 times a. But we know that the limit of the nth root of any number, right, any real number, positive number, is 1, right? So this limit will be a. Okay. So that's good. So what happens, that's kind of the easy version, right? So we're gonna get something like that. So let's suppose now that a is greater than b, right? So that's one of the other possibilities. Now the limit when n goes to infinity of the nth root of a to the n plus b to the n, right? And then what I can do is I can take common factor a to the n here, right? So then we have the limit when n goes to infinity of the nth root of a to the n, and it multiplies 1 plus b to the n over a to the n, okay? And I'm doing this because b is smaller than a, and so this thing will go to 0, okay? So you will see now. So you have the limit when n goes to infinity of a times the nth root of 1 plus b over a to the n, right? Now when n is very large, this 1 plus b over a to the n is very similar to 1, right? Because this thing is going to 0, right? So this is the limit of a number, right, that is very close to 1, but we know that the nth root of any number, right, is going to be 1. Okay, so this limit is a. And the other possibility is if b is greater than a. But in this case, it's kind of the same thing that we have done, but we can exchange the roles of b and a, right? You can see, you can do everything here as well, and with a over b here and b out, and so the limit here will be here nth root of a to the n plus b to the n. It will be b, okay? So this limit, let's call it L, will be the maximum of a and b, right? If a is greater than b, will be a. If b is greater than a, it will be b. And if they are equal, it doesn't matter, right? Because it doesn't matter if it's a or b. Okay, that's the first one. Let's go for the second one. The second one is harder, actually. So we have 2. The limit when n goes to infinity of the nth root of a plus the nth root of b over 2 to the n. And again, a, b are greater than 0. Now this limit, if you actually do the limit of this to this, you have the limit of this is 1 plus 1 over 2 is 1, and then the limit of n is infinity. Okay, so this is one of those limits 1 to the infinity, and this is an indetermination, and we know that this will be of the form e to the c, where c is the limit when n goes to infinity of n, and then the nth root of a plus the nth root of b over 2 minus 1. Okay, that's c. That's the thing that we want to compute now. And now the difficult part is to compute this thing, right? So we have the limit when n goes to infinity of n, and then we have, let me do this trick, a minus 1 over 2, and then plus the nth root of b minus 1 over 2, right? So we can separate these two limits. As you can, if you can see, this is n times the nth root of a minus 1 over 2 plus the limit when n goes to infinity of n times the nth root of b minus 1 over 2, right? So these are basically the same limit. The only thing that changes is that a here and we have b here, right? So if we compute this thing, we will know both things because we just need to change the result here in terms of a. We will just need to express it in terms of b, okay? So let's compute that first limit, okay? N over 2 times the nth root of a minus 1, okay? Now this is a hard one, okay? If you had, you know, later on in the course we will see like Taylor expansions or L'Hopital rule, and you can actually apply it here and find the result pretty quickly, right? Because what we have here is this is going to 1, so this is 1 minus 1 0 times infinity, okay? So another indetermination. So here we have to apply a trick and some of these asymptotic equivalences. Okay, so then we have, let me express, this is the nth root of a is a to the 1 over n, right? But we can express this like this. This is e to the 1 over n logarithm of a, right? So this is one way of writing things, okay? Now, or let me see, this is e to the logarithm of a divided by a, okay? You could write it like, get the n inside, so you have the logarithm of the nth root of a, but we're not interested in that, right? But we know now, so we have here, we have the limit when n goes to infinity of n over 2, and then we have e to the logarithm of n minus 1. Now we know that, logarithm of a over n. We know that e to the epsilon sub n minus 1, when epsilon sub n is going to 0, is something very small. This is asymptotically equivalent to epsilon sub n, right? Let me see. So now here, our epsilon sub n is going to be the logarithm of a over n, right? This is something that's going to 0 as n goes to infinity. So in these limits, if you were multiplying n over 2, we can substitute here actually the limit when n goes to infinity of n over 2, and instead of writing e to the epsilon sub n minus 1, we write epsilon sub n, which is the logarithm of a over n, right? So this is n and n go away, and we have 1/2 of the logarithm of a, which in other words is the logarithm of the square root of a. Okay, that's the limit that we wanted to compute. Okay, and for that we have used this asymptotic equivalence. Okay, so here this is the logarithm of the square root of a, and this, as you can see, this will be the logarithm of the square root of b, obviously, right? So then the result of this is the logarithm of the square root of a times b, right? Because the sum of the logarithms is the logarithm of the product. So then this is c, and so our limit is e to the c, e to the logarithm of the square root. The actual limit is the square root of a times b. Okay? Okay, let's go for 3. Let's do 3. 3 is the limit when n goes to infinity of n times the square root of n squared plus 1 minus n. Okay? So here is infinity, and then this thing minus this will go to, this is infinity minus infinity actually, so we don't know. Okay, this is an indetermination. Now whenever we have this thing, okay, the square root of something minus something, the way we deal with this is we multiply by the converse, which is the expression that's the same, but instead of subtracting is summing, and divide by it. Okay, so if you multiply and divide by the same thing, if it's not 0, you have the same expression. And then in the numerator, this is a minus b times a plus b. So you have the difference of the squares, a squared minus b squared. A squared is n squared plus 1, and then b squared is n squared. And here you have n squared plus 1 plus n. Or in other words, 1 over the square root of n squared plus 1 plus 1. Okay, so we can substitute here. Right? So this is the limit when n goes to infinity, and we get n in the numerator, and then the square root of n squared plus 1 plus n, right? Now if we divide everything by n, we have 1, and then we have 1 plus 1 over n squared, okay? We can see this if we have a common factor n squared, right? And this, if we divide by n, then this is the same as dividing this n squared by the square root of n squared as well. Okay, so what you're left with is 1 plus 1 over n squared. Okay, here. And then here we have plus 1, right? So now the limit of this is the limit of 1 divided by the limit of this plus the limit of this. But this is 1, right? The limit of this. So we have 1 divided by 1 plus 1, 1 half. Okay? Another way to see it is to say that the square root of n squared plus 1 is asymptotically equivalent to the square root of n squared when n is large, which is equal to n. So here this limit will be the same limit as n over n plus n. So you have n divided by 2n, which is 1 over 2. Okay, so the same thing if you know your asymptotic equivalences. Okay, so whatever you prefer. Okay, let's go for 4. 4 is the limit when n goes to infinity of the square root of the fourth root of n squared plus 1 minus the square root of n plus 1. Okay, so this is the same thing as before, but instead of having the square root, we have the fourth root. Okay, so there are two ways you can do it. You can either apply this rule 2 times, so you have the fourth root of n squared plus 1 minus this times the fourth root of n squared plus 1 plus this, and you will get something with square roots in here, right? So let me see. This is the difference of the squares. You have the square root of n squared plus 1 minus n minus 1, and then this is the fourth root of n squared plus 1, or let's call this n plus 1, plus the square root of n plus 1. And then you can do the same. You can multiply and divide by let me see, this is fourth root plus square root of n plus 1. You can multiply and divide by the converse of this, which is the square root of n squared plus 1 plus n plus 1. And here we have the difference of the squares. We have n squared plus 1, and you have minus n plus 1 squared, which is minus n squared minus 2n minus 1. Okay, and so what you're left with is minus 2n over, and then the fourth root of n squared plus 1 plus the square root of n plus 1 times the square root of n squared plus 1 plus n plus 1. Okay, now you substitute here. Okay, so that's one way of doing it. The other way of doing it is to apply that formula that we saw in Unit 1, right? In exercise, I think it's problem 1.6, which is that x to the, let's say, a minus y to the a is x minus y times the sum from k equals 0 to, is it 0? It's 1. K equals 1 to the a of x to the a minus k, and then b to the k minus 1. Or in other words, if you want to expand it, you have x to the a minus 1 plus x to the a minus 2 b plus blah 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 plus a, sorry, not b, sorry, this is y here, y, and then we have x times y to the a minus 2 finally plus y to the a minus 1. Okay, but here a is 4, right? And then so we have x to the 4 minus y to the 4 is x minus y times, and then you have x cubed plus x squared y plus x y squared plus y cubed. Okay, and if I erase this, so my x here is the fourth root of n squared plus 1, and y is n plus 1, right? So x to the fourth is n squared plus 1, y to the fourth is n plus 1 squared, right? So what we have here is you have to solve for x plus y. You have x to the fourth minus y to the fourth, and you have x cubed plus x squared y plus x y squared plus y cubed. And in the denominator you have, sorry, in the numerator you have x to the fourth minus y to the fourth, which is here what we have. And in the numerator, in the denominator, you have this expression, which if you expand this, you will see it's the same thing. Okay, so either way works, both ways. Okay. Okay. So let me substitute this here. So we have minus, and then let me express this is minus 2n times the square root of n. So this is n to the 3 halves. Okay. And then we have the fourth root of n squared plus 1 plus the square root of n plus 1, and we have the square root of n squared plus 1 plus n plus 1. Okay. Now let me see what I can do with this. This is asymptotically equivalent to the fourth root of n squared, which is in other words, this is the square root of n, right? And so, and the square root of n plus 1 is asymptotically equivalent to the square root of n, right? So this thing is asymptotically equivalent to, let me write it here, 2 times the square root of n, right? And then this here is n squared plus 1 is asymptotically equivalent to n, and then n plus 1 is asymptotically equivalent to n, right? So these two things are 2n, right? So then we have n to the 3 halves, sorry, this is the limit when n goes to infinity, and here the limit as well when n goes to infinity. And let me erase this thing here. Okay. So this is equal, and then you have to n to the 3 halves divided by the square root of n times n is 1, right? So this is the limit of minus 2 over 4, in other words, minus 1/2. That's the limit. Okay. So one word of warning here. I've used these asymptotic equivalences because, you know, n squared plus 1 is negligible with respect to n squared, right? We can do that here, neglect those terms because we're summing things. Okay, if we were so for instance, if you do it here, right, and you say, well, using this is asymptotically equivalent to square root of n minus square root of n, the limit is 0, right? But that's what you can't do, okay? Because the thing here is when you subtract these things, it's obvious that the most important terms, which are the square root of n, will cancel out, and the limit actually depends on the smaller terms that you are neglecting here. Okay, so that's what you have to be aware of and wary when you are computing limits with subtractions, right? But if you sum two things, that's okay, because if you sum two things of the same order, the smaller terms will not be relevant at all. Okay, so you can neglect them. Okay, so you remember that you can neglect terms when you're summing things and when you're dividing and multiplying, but not when you're subtracting. Okay, that's the trick. Okay, let's see. Let's do. Well, you could also do like divide things by, you know, the if you divide, this is n squared, and you have 1 plus 1 over n squared, right? And you divide everything by the square root of n something, then this cancel out. And you could do that like we did in the previous in part 3, right? You would arrive to the same result. Okay. Now let's do part 5. This is the limit when n goes to infinity of 2 to the n plus 1 plus 3 to the n plus 1 divided by 2 to the n plus 3 to the n, right? Now, here the obvious thing is to see that we have seen that in rational functions, the leading term, the term that's growing the fastest, in this case is 3 to the n plus 1, is the one that will be determining the value. Okay, so what I'm going to do is I'm going to divide everything by 3 to the n, right? So I have 2 times 2 over 3 to the n plus 3, and then we have 2 over 3 to the n plus 1. Now we have the limit of this is going to 0, right? Because this is smaller than 1, and so the powers of something that's smaller than 1 as n goes to infinity goes to 0. This is going to 0 as well. So the limit of this is 3, right? And so this is a very similar to the first one, where we divided by the first term, right? We could also say that because 2 is smaller than 3, this implies that 2 to the n is actually negligible with respect to 3 to the n when n is large. So we could rewrite this limit as 3 to the n plus 1 divided by 3 to the n, right? Because we're getting rid of the negligible terms, and the result is 3. Okay, so both things are correct. Actually, this is the kind of reasoning that allows us to do this. Okay, so that's the rule behind it. The kind of thing that, you know, if something is negligible in a sum, you can divide it by the other term, and you will get something that goes to 0, right? And then finally, the limit when n goes to infinity of n squared plus 1, n squared minus 3n, n squared minus 1 over 2n. Okay. Okay, so the limit of this is going to be 1, right? And the limit of this is n squared over n. This is going to be infinity. So this is 1 to the infinity. So this is an indetermination of the kind e to the c. Okay, and here c, as usual, is the limit of this n squared minus 1 over 2n times n squared plus 1 over n squared minus 3n minus 1. Okay, and so now let's work with this n squared minus 1 over 2n, and then we have n squared plus 1 minus n squared plus 3n, right, over n squared minus 3n. And then we have here n squared and n squared cancel out. We have the limit when n goes to infinity of, let's see, we have n squared minus 1 times 3n plus 1 divided by 2n squared, right, because we can take a common factor in here, n minus 3, if I'm not mistaken, right? So then here, what well, we can expand this actually, but we can take care only of the large terms. Okay, so as usual, n squared minus 1 is asymptotically equivalent to n squared, 3n plus 1 is asymptotically equivalent to 3n, 2n squared is asymptotically equivalent to 2n squared, n minus 3 is asymptotically equivalent to n, right? So I limit when n goes to infinity, and then we can substitute. This is n squared times 3n, and we have 2n squared times n. Okay, so n squared n cancel out, and we have the limit of this is 3 halves. But so that c, the original limit, is e to the c, e to the 3 over 2. Okay, and that's the end of the problem.